In the last video, we talked about ionic bonding, in which electrons are donated from a metal to a nonmetal. In covalent bonding instead, electrons aren't being donated, they're actually being shared. So to understand how this works, we need to look back at electrostatic forces and why exactly this attraction between atoms occurs. Now, if you look at this diagram here that I have provided, what you should notice, and should be a review for you, is that positively charged entities repel each other. So, for example, if we were to be talking about, let's say, hydrogen atoms, their nuclei would repel each other, while their negatively charged entities, which would be their electrons, actually repel each other. And so, to form a covalent bond, there's this balance between the fact that the electrons from two different hydrogen atoms repel each other and the fact that the nuclei repel each other. Well, if that's the case, if that's the only thing that's at work, then hydrogen atoms shouldn't be able to get close to each other because they should repel each other. What actually happens is that the electrons of one hydrogen atom are attracted to the nucleus of another hydrogen atom. And so as a result, as you can see on this bottom diagram right here, there is a high concentration of electrons in between two hydrogen atoms because they're being attracted by the two nuclei. So there's a high concentration of electron density between these two nuclei, and that is actually a covalent bond. So it's not the traditional, the colloquial, we are sharing them, but instead this glue, this covalent bond, results from electrons being attracted to the opposite atom's nucleus. This graph is crucial in understanding covalent bonds because it demonstrates the ideal distance between atoms in order to maximize the attractive electrostatic forces that exist between the two atoms. So as you can see on this graph, on your y-axis you have potential energy, and on your x-axis you have internuclear distance. Potential energy, if it's above 0, that means that the atoms are repelling one another. There's a repulsion force. If it's below 0, that means there's an attractive force. So as you can notice, when your internuclear distance is 45, meaning your atoms are very close together, hydrogen atoms actually repel one another, and that's because their nuclei are too close together and positive charges repel each other. Now, as the internuclear distance increases, hydrogen atoms no longer are repelling each other until you get to R equals 74. At that point, that is the ideal distance in order to have the greatest attractive force between atoms. So that's at R equals 74. Now, that represents the bond length, so the distance between the hydrogen atoms, and it also represents, the 432 represents the bond energy, and that is the energy required to separate those hydrogen atoms. Now, if you continue increasing the internuclear distance, what you'll notice is that the potential energy starts to increase, meaning there is less attraction between the atoms until you get to the R equals 300. And at that point, the potential energy practically reaches 0. And the reason why is because of Coulomb's law. Now, Coulomb's law states that as the distance between atoms increases, the attraction between them also decreases. So as hydrogen atoms get farther and farther and farther apart from each other, they reach the point at which there is no attraction between the atoms. So you have, at the beginning of this graph, the atoms being too close, and as a result they repel each other, and at the end of the graph, if the distance is too great, then there is no attraction. And at the R equals 74 for hydrogen, that represents the ideal distance between the atoms to maximize attractive forces. I'm now going to talk about Lewis structures, which enable us to depict covalent bonding. I'm not going to teach you how to draw these yet. That will be later in this video. But I wanted to start off by talking about single bonds. As you can see in this example, if I have two chlorine atoms, what they're going to do in order to acquire an octet, 8 valence electrons, is they're going to share their 2 electrons. The first chlorine needs 1 more electron, the second chlorine needs 1 more electron, so if they share those 2 electrons, they will end up with both a perfect octet. Now, instead of drawing it like this, we often draw the sharing of two electrons with just one single line, and that is a single bond. So each line, each single bond represents two electrons that are being shared. Now, if we have a double bond, what that means is we are sharing two different pairs of electrons. So as you can see in this example, carbon needs to share two pairs of electrons with oxygen with each of the oxygens. And so as a result, you have two distinct lines, and so those two lines actually represent 4 electrons. Now, we'll actually go through and talk about how you know when you need a single, a double, and, as I'll get to in a second, a triple bond. But just for you to know that each line represents 2 electrons, so when you have a double bond, those 2 lines represent 4 electrons. And finally, you can have a triple bond, and so a triple bond represents the sharing of a total of 6 valence electrons. The next question that should go through your minds is, well, how does a single, double, triple bond, how does that affect the length of the bond? And as you can notice in this slide, as you increase the number of shared electrons, so as you move from a single bond in which 2 electrons are shared, to a double bond in which 4 electrons are shared, to a triple bond in which 6 electrons are shared, your bond length actually decreases. And that makes sense because there are more electrons that are being shared between the atoms, and as a result, those 2 nuclei are going to be pulled closer to one another. In this section, we're going to be talking about bond polarity and electronegativity. In order to actually talk about the polarity of bonds, which we will get to, we need to define what electronegativity is. So electronegativity is the ability of an atom in a molecule to attract electrons to itself. Now notice electronegativity is different from ionization energy. Remember, ionization energy is the ability of an atom to lose electrons. Electronegativity is actually the exact opposite. It's the ability of an atom to attract electrons. Now, for trends, as you move down a group, the electronegativity decreases. And it decreases because the size of the atom increases. And so as an atom's size increases, its attraction for the electrons decreases as well. Now the trend for going across a period, keep in mind as you move across a period, your atomic size decreases, which means that the electronegativity would increase because the size of your atom is decreasing. Now that we've defined what electronegativity is, we need to talk about bond polarity. Now, the greater the difference in electronegativity between 2 atoms, the more polar their bond is. Now, the interesting thing is we've been talking about ionic and covalent bonding, and it seems like it's one or the other, but there's actually a continuum. If you have a very, very small difference in electronegativities, then we say that the bond is nonpolar. If there is a difference in electronegativities, but it's not significant, then we say that the bond is polar. And then as the difference in electronegativity continues to increase, you eventually end up with an ionic bond. And you can see that here. So notice F2, those electrons are being shared equally because you have 2 fluorine atoms. They obviously have the same electronegativity because they are the same atom, and so they're going to share electrons equally. H and F, fluorine is more electronegative than hydrogen, so as you can see, the red represents negative charge while the blue represents positive. So there is a difference in electronegativities, and therefore we say that the bond is polar. If you look at LiF, there is an even greater difference in electronegativities, and as a result, that difference is so large that we say that the bond is ionic, meaning that lithium not only does not share the electrons, in fact, it ends up donating the electrons because the electronegativity of fluorine is so large that it actually steals an electron from lithium. Now, the reason why we have a partial positive and a partial negative charge on hydrogen and fluorine respectively is because an electron is not actually donated to fluorine. Instead, fluorine, because fluorine has a larger electronegativity, it hogs the electrons, but it does not completely take or accept the electrons. And so as a result, we say it has a partial negative charge. Another way of representing that is with an arrow. That arrow demonstrates that fluorine is more electronegative than hydrogen. Okay, and that's actually a vector. Notice the cross goes above hydrogen, meaning hydrogen is partially positively charged, while the arrow is towards fluorine, which means that fluorine is partially negatively charged. Dipoles are created when two electrical charges of equal magnitude but opposite sign or charge are separated by a distance. So as you can notice for hydrogen and fluorine, a dipole has been created because hydrogen has a partial positive charge and fluorine has a partial negative charge. Now the quantitative way of expressing a dipole is the dipole moment. Now the dipole moment equals the charge, Q, times the distance between those charges, the R. So in order to draw a Lewis structure, we need to follow these 5 instructions, and then it's actually quite easy. So the first thing we need to do is sum the valence electrons from all the atoms. So in the example that I've provided you, you have CO. So let's actually count the number of valence electrons. Carbon has 4 valence electrons, and oxygen has 6. So my total number of valence electrons in this problem is 10. Okay? Now I need to write the symbols for the atoms to show which atoms are attached to which and connect them with a single bond. So in this case, since I only have 2 atoms, I actually don't have a central atom. It's just carbon bound to oxygen. Okay? As easy as that. Then number 3, complete the octets around all the atoms bonded to the central atom. Well, I don't have a central atom, so I am just going to complete the octet. If, for example, I had another oxygen coming off right here, then I would complete the octet for the 2 oxygens, and then I would finish carbon. But in this case, I don't have a central atom because I only have 2 atoms. So carbon has 2 electrons here that it is sharing with oxygen, so it needs 6 more. So 2, 4, 6, 8. Oxygen needs 6 as well. Okay. And since I don't have a central atom, I'm going to skip number 4. Number 5 says, if there are not enough electrons to give the central atom an octet, try multiple bonds. So let's see, I can use a total of 10 valence electrons. In this case, I have 2, 4, 6, 8, 10, 12, 14. So I'm using way too many valence electrons. I can only use 10. So what I'm going to do is I'm first going to create a double bond and see how many valence electrons I end up using if I have a double bond. So I'm going to double bond carbon to oxygen. So that's 4 electrons there, which means carbon needs 4 more. Oxygen needs 4 more as well. So now I have 2, 4, 6, 8, 10, 12 valence electrons. Well, I can only use 10. So what that tells me is a double bond is not enough. I need a triple bond. So I'm going to triple bond carbon to oxygen. So that's 2, 4, 6. I'm going to put 2 electrons here and 2 electrons there. I'm following the octet rule, and I'm only using 2, 4, 6, 8, 10 valence electrons. So this right here is my Lewis structure for carbon monoxide.